Okay, this is problem 1289, or excuse me, 1389. The question would be, do you need to draw a free body diagram? In order to do that, you would ask the question, how many degrees of freedom? You'll find out that it's 1 degree of freedom. Because it's 1 degree of freedom, if you're given any angle, you can find all other positions. If you're given a single dot term, you find all other single dot terms. And also, given a single double dot, in this case theta double dot is 0, then we can find all other double dots. So we can find the accelerations that we want for this. Question though is to determine the force from the curved rod onto the collar. So because we need the force, we also need to measure or to draw the free body diagram. So we're going to start with drawing the free body diagram. There are 3 forces: gravity, and the 2 forces coming from the 2 bars OA and the curved bar. So I'll draw those in. I'll do a dashed line to show where the straight bar is, and the angle back here would be actually the angle from here is theta. Alright, so the normal force from that rod is going to be perpendicular to it. So I'm going to draw it in perpendicular to that line. The other force is going to be perpendicular to that curved surface. So I'm going to try and draw that surface in as a dotted line just to get my bearings. So that's the curved surface, and the force from there is going to be perpendicular that surface as well. So let's call this force from the S, because it's the one from the straight bar, and we'll call this force C because it is the force from the curved. So that's my free body diagram. Okay. The next thing after drawing the free body diagram is to think about what coordinate system you want to sum forces. And to do that, you should be thinking about which coordinate system you want to use that will make your accelerations relatively easy. In this particular case, we have a formula for R. We're given thetas and theta dots, so it seems reasonable to me that you would choose the R and theta directions. So what I'm going to do is just draw dotted lines to make sure that we understand which way the directions are that we're going to sum forces. So to get the R and the theta directions, the first thing you do is draw a line from the origin where you're measuring the R and theta through the particle, and so straight out. So in that case, your R is actually right here. It's parallel with that dotted line that was drawn from the origin down here to the particle right there. Right, so this would be the UR direction. That's your radial direction. It's not a force, it's a radial direction. So I try to draw it off center just a little bit. The other direction is the theta direction. It'll be perpendicular to UR, and it is rotated 90 degrees in the direction of positive theta. You can see that positive theta is counterclockwise, So if you go counterclockwise on the UR, you're going to get the U theta. So I'll draw that in up here as well. So this is the U theta direction. Notice that the U theta direction is parallel with the S force, but it is not parallel or perpendicular to the C force. The C force is coming perpendicular to that curve, and that curve is at some odd angle. So one of the things that I'm going to have to do is find the angle of that circular path so that I can get the angle for the C. In order to do that, you're going to find the tangent in the R theta direction, and that'll get you the angle for that force. We'll do that a little bit later. Let's do the things that are obvious and basically the same thing. So let's get the acceleration terms. Okay, so since I've decided to use R and theta, I can write down the acceleration terms. The acceleration is R double dot minus R theta dot squared in the UR direction plus 2 R dot theta dot plus R theta double dot in the U theta. Okay, so for this formula, I am given theta, given theta dot, and I'm given theta double dot. So that's not a problem. What I need to find, though, are the R's, the R dots and the R double dots. Okay, so they give me a formula for the R. They say that R is equal to, because of the circular path, it's 1.5 times, parentheses, 2 minus cosine of theta in feet. So what I'm going to do is take a derivative of this thing with respect to time. So I'm going to have 1.5 times the derivative of the cosine is minus sine, so that'd be in the plus. So this is a sine theta, chain rule, theta dot. For the second derivative, this is a product, so I'm going to take the derivative of the first term. Derivative of the sine is the cosine, along with the chain rule, and then I multiply it by the second term. Then I add the first term times the derivative of the second term. So there's my R dot and my R double dot. Okay. So I can plug numbers into that. If you do, what you'll find is that the R, you're going to put in theta equals 120 degrees, which was given. Theta dot was 5, and theta double dot is 0. So what you'll have when you plug those numbers in is R will equal 3.75. You plug in the theta 120, theta dot, which is 5, and you'll find that R dot is equal to 6.495. r double dot, you plug in and you get r double dot is a minus 18.75. Now the only thing that's left is to sum the forces in the r and the theta direction and set them equal to mass times acceleration terms, which you already have. The only problem right now is that you don't know the angle for that body, or the force C. So what we need to do is to find the tangent of the curve that it's on, and that gives us the angle for the curve, and then we can find the normal from that. So that's what we're going to do next. Okay, in order to find that angle between the force C and the r and theta coordinates, you might want to look at the formulas that were derived on page 145 of the text. If I could summarize for that, let me draw another picture that's separate from the free body diagram, just showing directions so that we can get our bearings. Essentially, you have a curved surface, something like this. So this is the curved surface. I'm going to exaggerate what's happening, but then you'll have a UR direction. So let's say the UR direction is off like this. This will be the UR. The U theta is perpendicular to that. So I'm just drawing it down here. Here's the U theta. Okay, so I'm kind of exaggerating the geometry just to make sure it's reasonably clear what the angles are. Okay, now there's a tangent to this curve. Let's see if I can draw it in there forever. Okay, there's the tangent to the curve. Turns out that the angle between the UR and the tangent, so I'll show it like this. So it'll be this angle, let's see, between UR and the tangent, right there. Okay, the book likes to call it psi, so I'll call it psi. That angle between the UR and the tangent can be given as, using this following formula. The tangent of psi is equal to the radius divided by the derivative of r with respect to theta. And again, I say that's on page 145. Where he describes that. So I'm not going to try to derive that formula, I'm just going to use it. So what I'm going to do is try to find that angle psi. And incidentally, the force, let me kind of draw that force in here to this diagram. The force is over here, right? Trying to get it perpendicular to that tangent. So it's not really, this would be the force C that I'm calling it. It's perpendicular to the tangent. So this angle psi is not really the one I'm looking for. What I want is, I would like 90 minus psi, which will get you this angle right in between here. Once I'll find the psi, and then I'll take 90 minus psi to get the angle between the force that I'm talking about and the UR direction. Okay, so let's do that. First thing we're going to do is we're going to find dr d theta, which is not the same thing as the time derivative. All right, so here we go. We're going to come back over here, and we're going to say dr d theta, which is different than the dr dt. It won't have a chain rule. All right, so dr d theta is equal to, looking back on the notes, okay, it's equal to 1.5 times the sine of theta. Alright, so that's dr d theta. And The R I've got from before. I'll just write it down again. R is, let's see, it's 1.5 times 2 minus cosine of theta. So what I know is that the tangent of psi is equal to 1.5 times 2 minus the cosine of theta divided by 1.5 sine of theta. Alright, so basically I have everything I need. I've got these numbers, and so I'm going to plug values in. If you plug in theta equals 120, the tangent of psi turns out to be, well, apparently there was a little bit of a glitch. I'm not quite sure what happened, but let me move on. So I'm finding the tangent of psi. I took the r in the numerator. In the denominator, I'm taking this derivative that I took, 1.5 times the sine of theta. Right, so now I can just plug numbers in. Angle theta is equal to 120. So that plugs in here, and it gives me that the tangent of psi is 2.88. If you take the inverse tangent of that, you find out that psi is 70.9. Let me put it someplace where it fits. So psi will equal 70.89. So 90 minus psi, which is the one that I really want, is going to equal 19.11. Okay, so now that I have all of these angles, I'm going to come back up here, find a little bit of room, and I'm going to sum the forces in the UR direction and in the U theta direction as well. So when I do, I have, I'm looking at my free body. Okay, so I have in the R direction, okay, so for the R direction, I'm going to have C times the angle of, let's see, that would be the cosine of the angle 19.19, 19.11. I also have part of the mg, which is pointing in, so that would be minus mg. His angle is going to be 120 minus 90, which is 30, and that would be a 30. That'd be a cosine of 30. There are no other forces in the R direction, so this is equal to mass times the acceleration in the R direction, which is R double dot. I have it written down elsewhere. R double dot minus R dot R theta dot squared, excuse me. Theta dot squared. I know the R double dot, I know the R, the theta dot, so I can plug into that. In the theta direction, I have a negative C sine 19.11. I I also have a plus mg sine of 30. It's all of the forces that I also have a plus s. That's all of them, and so that equals mass times acceleration in the theta direction, which is 2r dot theta dot plus r theta double dot. So I know the r dot, r double dot, theta dot, theta double dot. I know the mass, I know the g, I know everything except c and s. So this gives you two equations that you can solve for the two unknowns. If you plug everything in, you should end up with the forces of, let's see, let me check my notes here. The S turns out to be 2.77 if I'm not mistaken. So the S ends up being 2.77, and the C, the one that's coming from the curve, is, I think I have those backwards actually. I'm looking at my notes. .605. Yep, I got that backwards. 605. So I think, let me pause and back up and get this right. Let me check my notes. Be back shortly. Okay. Yeah, I did have those backwards. I was calling them something else by a different name in the notes. Okay, so the S, the one that's coming from the straight slot, when you plug numbers in, comes out to be .605. Positive. The other one, off the curve, comes out to be a negative 2.77. And negative means that I drew it incorrectly. The way I drew it was that circular slot was holding it out away from the center, but in fact the negative tells me I'm wrong, that the C is actually pulling it inward. So there's a force that's pulling the collar inward as it moves around. So that's the end of this particular problem. I'll post this for you.